Okay, let's humble ourselves and we pray. In the name of the Father, and of the Son, and of the Holy Spirit.
Amen.
Amen. Hail Mary, full of grace, the Lord is with you. Blessed are you among women, and blessed is the fruit of your womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and the hour of our death. Amen. Glory be to the Father, and to the Son, and to the Holy Spirit, as it was in the beginning, is now, and ever shall be, world without end. Amen. Light in our minds for excellence. In the name of the Amen.
Amen. In the name of the Father, the Son, and the Holy Spirit. Amen. Thank you very much, Sandra. I don't know where these people are. I think they are still eating. They are still doing what? I don't know. But last time you did not make it, I know. Had some issues there and there. But today we are going to look at, I wanted us to finish this part of refraction, of what? Refraction, this first part, and then later on we shall look at prisms. So we looked at, last time we looked at real and apparent depth, and we were able to go through this. We went through this with you, and we looked at some of these applications, the appearance of the sun at the west. Why is it that we have a longer day than the night? We looked at that. We looked at this. I told you to read this. This is just you have to read, and then you get to know that here there will be the rays of this stick are going to be bent due to refraction. So there will be an apparent position, and you see the stick as if it is near to the surface of the water, but all this is all about refraction. Even in the fish's eye, or the apparent size of the fish. So you may see the fish when it is large, but indeed it's not large. So the reason may be due to the refraction. And there is an exercise which I left here. So some of your friends have tried out the numbers. They've tried out some numbers and I've marked. I think I've received only 2 people have sent in their work. And I've tried to mark that work actually something like 5 minutes back. So today we are going to look at total internal reflection and the critical angle. That's what we are going to look at. So you have these questions, go through them, check yourself whether you are competent. And if you feel you are competent, if you're revising for exams, better you revise going backwards. Where you have stopped, you read going backwards, testing yourself with these other questions which are at the back here. Do you still remember how you can do such questions? I can draw ray diagrams. So revise as you go backwards. Can you prove out the Miller formula like that? So you keep on revising, but as you go backwards, keep on you check yourself whether you still remember what you learned some time back. So we are going to look at total internal reflection, and this is still also an O-level concept that you have already studied some time back or 3 years back. What's total internal reflection? For these ones, I will just explain where I need to write. We shall reach where I need to write, and I will write. So we can discuss this, and then afterwards we shall write later on. But you have these notes, so you write them later. So total internal reflection, they're saying that this one normally occurs when the ray of light is traveling from an optically dense medium to a less dense medium. And the angle of incidence must be greater than the critical angle, So it is a reflection, total internal reflection. We are under refraction, but we are looking at total internal reflection. So it is a reflection within a dense medium when the angle of incidence when the angle of incidence in the dense medium exceeds the critical angle, or when the angle of incidence exceeds the critical angle in the medium. That's what we call total internal reflection. So the ray of light will bounce back into that same medium, causing a reflection within that same medium. For instance, we have seen if you have water and air. So if a ray of light is coming from water and it is entering air, so there will be total internal reflection if the angle of incidence exceeds the critical angle. So there is the term critical angle. And what do we understand by the term critical angle? Let us first watch critical angle, then we shall come back to this. So critical angle is the angle of incidence. I'm here at this point. Critical angle is the angle of incidence for which the angle of refraction is 90 degrees. So it's the angle of incidence, for which the angle of refraction is 90 degrees for a ray of light traveling from an optically dense medium to a less optically dense medium, So water and air. Water is more dense compared to air, or glass and air. Glass is more dense compared to air. So the ray of light will be reflected back into the glass. Why? Because glass has a highest optical density compared to air, and it will be reflected, that ray of light will be reflected if and only if the angle of incidence is greater than the critical angle. And we have said what critical angle is. So critical angle to occur, there must be an angle of incidence, an angle of refraction, which is 90 degrees, So here, initially they are saying that when a ray of light is coming from glass entering air, and when the angle of incidence is not greater than the critical angle, it is less than the critical angle, two things will happen. One, that ray will be reflected into the same medium. So this ray be reflected into this same medium, and also that ray will be refracted in the other medium, which is air. So that happens when the angle of incidence is less than the critical angle. So you can summarize that somewhere. If you're trying to write a summary of what we have just said, you can summarize that and say that when let's say when the angle I is less than, when the angle I is less than, this is angle is less than the angle C. So there are things that will happen, or you can say when I is less than C, things that will happen. Number one, two things will happen. So the ray of light is reflected, is partially reflected into the same medium. And two, ray of light is partially refracted in the other medium. So, and now we are talking about whereby these rays, one is less dense and another one is more dense. So that's what we are talking about. So one is, so we shall have this, something like that, and then like that. So this is I, this will be I also, and this will be R, something like that. So it will be partially reflected and partially refracted. This is, if this is the dense, and this is the less what? The less dense medium. So you have those two differences there, like that. That is the first scenario that will happen when the angle of incidence is less than the critical angle. Now, from number 2, if we go by the notes here, if the angle of incidence is gradually increased, the angle of refraction also increases. So the moment you increase, how do you increase the angle of incidence? By moving this red side. So if the angle of incidence is gradually increased, also the angle of refraction is increased. At a certain point or a certain value, the angle of incidence, the angle of incidence, at a certain value of the angle of incidence, the angle of refraction. Members, can you hear me?
Yes.
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 Emma, please, Emma, increase on your microphone. Increase on your speaker. That's when you'll be able to hear me. Otherwise, me, I'm loud and clear. Very, very clear, loud and clear. Everyone can hear me very well. So when the angle of incidence now is gradually increased at a certain instant, also the angle of refraction keeps on increasing and it reaches 90 degrees. At that point, the refracted ray grazes the surface of the medium, and we say that the glancing angle or the refracted ray, the refracted angle is going to be 90 degrees. So 2, you have to know that when the angle of incidence is increased, then the angle of refraction also increases. The angle of refraction also increases. So at this point, the refracted ray grazes the surface at an angle of 90 degrees. Then the angle I is what we call the critical angle. So when I equals to C, or when the angle of incidence is the critical angle, what will happen there is that we shall have this ray. Suppose that is the boundary of that ray like that. It has been increased. So we shall have this ray, refracted ray, grazing the boundary in that form. And this angle here will be the critical angle. So this will be the less dense medium, and this will be the more dense medium, And this angle is 90 degrees, which is the angle of refraction. So here what you have to note is that the angle of incidence is equal to the angle of is equal to the critical angle, is equal to the critical angle. And there we say that the angle of refraction, or that we can say that the refracted ray grazes the boundary at an angle of 90 degrees. The refracted ray grazes the boundary at an angle of 90 degrees. Then the angle of incidence is what we call the critical angle. Okay. Then the moment we keep on increasing the angle of incidence, maybe to a certain point whereby it exceeds the critical angle. So when I is greater than C, so when I is greater than C, when the critical angle is far greater than, you know whether you can see the things? Oh, my camera is not there. So when the angle of incidence increases beyond the critical angle, then total internal reflection will take place. So how do you have that? Like this. So I'm just giving you a summary of this. So the critical angle, the angle of incidence has been increased to that point. And what we shall get from there, then we shall have the ray being reflected within that same medium. At this point here, this is the angle of incidence, but that angle of incidence is greater than the critical angle. It's greater than the critical angle. Okay. So that's what we are seeing here. This is what we are seeing here, and it's what I've tried to draw. So let us summarize that. What are they saying? They are saying that when the angle of incidence is further increased, so this one illustrates, this one shows, let me zoom out a bit. This one shows that the angle of incidence is greater than the critical angle, which has been increased. So if the angle of incidence is increased beyond the critical angle, then the light ray becomes totally internally reflected back into the more optically dense medium. So the first thing you have to know is that the angle of incidence is greater than the critical angle. Then the other thing that you have to note is that the ray, you can say the ray is reflected back into the dense medium. So in other words, you can say hence i.e. total internal what? Total internal reflection takes place. Total internal reflection takes place. So if this is the dense medium and this is the less what? The less dense medium. So you have something like that to show you that the ray of light will be refracted or totally internally reflected in that form. Okay, so we have already defined what critical angle is, and we have also defined what total internal reflection is. If you have not understood what total internal reflection is, we said that total internal reflection, this happens when a ray of light within a medium is reflected back into that same medium when the angle of incidence exceeds the critical angle, or when the angle of incidence is greater than the critical, angle. And then critical angle is the angle of incidence for which the angle of refraction is 90 degrees for a ray of light traveling in a more optically dense medium to a less optically dense medium. So you can check with the notes there. All the notes are here, so you can be able to write it there. Okay, so get to know the definitions. Get to know the definitions very well. Understand the definitions of total internal reflection. Total internal reflection. You state the definition, and also you should be able to state the definition of critical what? Of the critical angle. Okay. Then the other thing that you should take note of, the other second thing you should take note of is the other conditions for total internal what? Total internal reflection. What are the conditions for total internal reflection take place? There are quite two conditions, and we have already seen them. One of them, of course, it is here, the angle of incidence in the optically dense medium is greater than the critical angle. That is the first condition. So angle of incidence, angle of incidence in a more optically in a dense medium is greater than the what? It's greater than the critical angle. So that is the first condition. And then the other condition is that the ray of light must be traveling from a more optically dense medium to a less optically dense medium. So 2, the ray of light travels from a more optically dense medium to a less You can understand what I've written there very well because I'm writing very fast in the interest of time. Okay. So those are the conditions for total internal reflection to take place, and you should put them on your fingertips because they are very important. Now, the ray of light must be traveling from a density. Okay, here they are giving an example, for example, glass and to water. So what is the relationship between the critical angle C and the refractive index N? So as I've just drawn for you, now we are going to use the scenario whereby we use the critical angle, where the angle of refraction is 90 degrees, and we develop a relationship between the relationship. So the relationship between the critical angle and the refractive index. So what we are going to use, this kind of scenario that I talked about, this part here, where I is equal to C, and then we develop that relationship. So you should know that at that point there, the angle of refraction is 90 degrees, and the angle of incidence is the critical angle. So the ray of light glazes, the refracted ray glazes the surface if the ray is traveling from a more dense medium than to a less dense medium. Okay, I did not write like that, but some time back I changed the handwriting. So you should draw one straight line. This is not correct here. When you have this, is not right. Okay, so I have to draw one straight line there. So what will happen is that we shall apply here Snell's law, let's say at this point here, at the point of incidence, we shall apply Snell's law. And we shall say that because it's coming from this, let's say this was glass and this is air. Okay, so we shall say that N glass, then sine C equals to N air, then sine 90, like that. Okay, now for N air is known as 1. So N glass sine C equals to 1 times sine 90. Of course, sine 90 is 1, and we have N sine C. Now, if you want to find the refractive index or the critical angle, then you make 1 a subject. So if I want to find the critical angle, then I'll say sine C equals to 1 over Ng. Or I can say Ng equals to 1 out of sine C. And both of these ones are the ones that show the relationship between the critical angle and the refractive index. I'll put you in the waiting room, Damira. You keep on playing music. Damira, watch out, my friend. And what's wrong with you? If I mute you, don't accept. Okay. So there are examples which are there. Maybe I can go through number 1, but I'll skip number 2, and I'll go. Maybe I can go through number 1. Number 1 is very easy. So let's go through number 3. Number 3 is the one which has a bit some challenging thing. But others also you can do them. It's a matter of substitution, and then you find the values there. So let us go through question number 3. They are saying that The figure below shows monochromatic light X incident towards a vertical screen. So they're saying that when the semicircular glass block is placed across the path of the light with its flat surface or with its flat face parallel to the screen, a bright spot is formed at A. What are they saying here? They're saying that before this semicircular glass block is rotated, its face, this face here we are seeing is parallel. In other words, it is straight. If I may use here some, let me see. It is straight. So let me use some pencil here and I try to draw. So it is straight. It is straight like this. It is parallel and it is straight like that. So before it is rotated, it is straight. And then after rotating, something is going to happen. So I'm saying when a semicircular glass block is placed across the path of light, with its flat face parallel to the screen, a bright spot will be formed at A. That is good. To be formed, it will be here. That's why these dotted lines show that there is a bright spot that was formed at A. When the glass block is rotated about the horizontal axis through O, the bright spot moves downwards. So when we rotate this, the bright spot shifts from point A to point B downwards, then just disappears at B, a distance of 1.68 centimeters from A. So when the moment it's at point B, just at point B, just beyond point B, it disappears. What does that one mean? Why does it? Actually, the first question is explain why the bright spot disappears. Why does it disappear when you rotate the block just beyond point B? So the reason is that total internal, the angle of incidence this time just exceeds the critical angle. In other words, actually, it's what I want to say. In other words, the angle of incidence is now beyond the critical angle, and the total internal reflection takes place. So that means that at that point there, at point B, the ray of light is just glazing the boundary, So grazing this boundary here like this. Just here they drew it poorly. Let me see if there are some diagrams here I can use. Shapes, where are shapes? There are no shapes here similar to that. Okay. So at this point here, actually here they drew it very well that now this semicircular block is just glazing the boundary like that, just glazes the boundary up to point B. So point B is just here. So beyond point B, beyond this point, when we keep on rotating, when we rotate this glass block in this other side, then it means that the angle of incidence is going to go beyond the critical angle, and now total internal reflection will occur within that block. So the reason why it disappears is because the angle of incidence exceeds the critical angle and the total internal reflection takes place. Then find the refractive index of the material of the glass block. So that's what they're asking. What is the refractive index of the material of the glass block? Maybe to be very genuine a bit, we can draw that diagram and then we see if we can find that. So I'll draw this. First zoom out a bit there. Then I'll draw this like that. Okay. Then I'll draw this like that. Then I'll draw this like that. Then this like that. This. Yeah. Yep. That is A, this is B, the light is there, and the normal is here, because the normal must be perpendicular to this block, to this surface, to this boundary. So this is the normal here. Okay. So the angle of incidence is the angle between the normal and the incident ray. So it is this one here. And that angle is now the critical angle because the refracted ray is glazing the surface. So it means that this angle which is here is 90 degrees. The angle which is here is 90 what? This one here is 90 degrees there. Okay, it is 90 degrees because that is the angle of refraction. Now, they say that the distance between the glass block and the screen, they gave it to us, it was 1.5. Okay, where is it? Somewhere. Screen from A. Okay, from the diagram, it's there 1.5. So this distance here, I'll call it 1.5. From here up to here, I'll say 1.5 centimeters. And also they said that this distance here is 1.68. So I'll call that 1.68. Okay, so 1.68 centimeters. Okay, so what do we need to do? So they're asking for the refractive index of this material. What's the refractive index of this material? Is what they're asking us to find. So how would we get the refractive index of that material? So we need to first calculate the critical angle so that we can use this formula of n glass sine C equals to the critical or equals to 1 or equals to NA sine 90, but NA sine 90 is 1. So this element here is what I'm talking about. So NG sine C is equal to 1. So for us to use that and find the refractive index of that glass, we must get the critical angle. So how do we get the critical angle? So what you should know is that the angle between this, this angle here, they called it theta, this angle theta. Okay, that angle theta, we should first find that angle theta. After finding the angle theta, then how are we going to get this angle which is here? This one here. We have to also get this angle which is here. This one here. So what is this angle? That angle is going to be 90 degrees, because if this is 90 here, it means that also this is 90. This one is 90 degrees. Obviously, that is 90 degrees. So C plus 90 plus theta shall be equal to 180. So let us first get theta first, and then we shall substitute in C plus theta plus 90 equals to 180 degrees. Okay. So from here we can say tan theta equals to the opposite, which is 1.68 out of the adjacent, which is 1.5. And theta is equal to the tan inverse of 1.68 up to 1.5. So automatically I don't have a calculator, but you can help me and get the answer to that. Brenda is off. Where? A. So C plus theta plus 90. So what do you get here?
48.2.
48. Sandra, 48?
Yes, 0.2.
0.2.
48.2.
Okay, 48.2. So since it is 48.2, so C, so we shall find C plus 48.2 plus 90 equals to 180. So it means that our C equals to, because this is 90, equals to 90 minus
41.8.
You get 41.8.
Yes.
Okay. So after getting C is 41.8, then we substitute in NG. Sine C equals to 1. And NG is what we want. So sine 41.8 equals to 1. So NG equals to 1 out of sine 41.8. And you get NG. What's the answer? Brenda,
1.5.
you get 1.1?
1.5.
1.5. Simple. So when you are calculating that, you need to go through your trigonometry very well. So let's proceed. Let's proceed. Okay, let me just pass through the things very fast, and then we go to this. This is the main thing here, because you have learned about this in P1. So applications of total internal reflection. They'll ask you, describe one application of total internal reflection. And that's the reason why you have these notes written for you. So you can say, they can state, they can ask, explain, or describe. So when they say state, you just list them: the formation of the mirage, formation of the rainbow, formation of light in optical, transmission of light in optical fibers, transmission of sky radio waves, and also transmission of light in prism binoculars. Now, formation of a rainbow, formation of a rainbow. You can research about this. Sandra, can research about how a rainbow comes all about. But mainly there is total internal reflection, but also due to dispersion of light, and that's why we have a rainbow. Now,
Yes, teacher.
you can research about formation of a rainbow. How does total internal reflection lead to formation of a rainbow? But I've told you that there are two things: total internal reflection and also dispersion of light there. So dispersion of light will be brought about by total internal reflection, but because it is white light, then each part, each constituent color will be refracted in its own, at its own angle, or at its own deviation. So forming a mixture of different colors. But when these colors overlap, they form what you call a rainbow. All right, formation of mirage. So normally mirage occurs on hot days. Now during hot days, the air next or near to the ground becomes very hot, so it becomes less dense, and the air above the ground, or that is beyond from the ground, is more dense. So remember that the ray of light is coming from the sun to the earth. So above the earth, the air is very cold, so it is a dense medium, and next to the earth's surface, the air is warm, so it is a less dense medium. So it appears as if a ray of light is traveling from a dense medium to a less dense what? To a less dense medium. So as light travels from the sky, as light travels from the sky, passes through various layers of what? Of air, and this light will be continuously or gradually refracted away from the normal, until a point is reached where total internal reflection takes what? Takes place. So the ray of light will be reflected away from the normal, gradually reflected away from the normal, until a point where total internal reflection takes place. So the observer, if this ray of light falls in the eyes of the observer will see an image of the sky, but it will appear as if it is a pool of water, an impression of a pool of what? Of water on the ground, but in reality, it is a virtual image of the sky. Brenda.
Yes, teacher.
Watch 10.
Yes, teacher. Yeah.
Okay, so don't see the water and say, hey, there's water. But normally this one happens on hot days, especially on tarmac roads, and you see a pool of water and you say, it's a pool of water. No. It is just an impression of the virtual image of the sky, but brought about by the total internal reflection. I've said that. What do you have to write? One, you say this one occurs on hot days. The air above the air next to the earth or next to the land is heated and becomes less dense, and the air above the earth is cold and is dense. So a ray of light traveling from the sky to the earth is gradually reflected until it reaches a point where total internal reflection takes place. So the observer receiving the totally internally refracted ray gets an impression of the pool of water on the ground, which is a virtual image of the sky. So optical fibers, you have only 1 minute and then you come back. Optical fibers, also these ones, they are made of a transparent material coated with glass inside. And these materials are used to transmit data, for example, communication. So when a ray of light enters into a pipe, strikes the boundary of the medium at an angle of incidence greater than the critical angle. So total internal reflection takes place at this point, at every point inside there. And this is repeatedly until in the pipe, this is repeatedly until the light becomes emergent from the pipe. So total internal reflection will occur within the pipe there because the ray of light strikes the inner surface of the pipe at an